In this video, we're going to find the oxidation state of carbon in several different molecules. In an earlier video, we've already seen the definition for oxidation state and also how to calculate it. So let's start with methane, and let's find the oxidation state of carbon in methane. One approach is more of a general chemistry approach where we know that hydrogen usually has an oxidation state of +1, and we have 4 hydrogens for a total of +4. The sum has to be equal to 0, so we know that carbon's oxidation state must be -4 immediately since we have only 1 carbon here. So let's go ahead and verify that with our dot structure. So remember, when we're calculating the oxidation state using dot structures, we're thinking about bonding electrons, and we know that each bond consists of 2 electrons. So we need to put in the bonding electrons for all of our bonds. Next, we think about the oxidation state for carbon, and we start with the number of valence electrons in the free atom, or the number of valence electrons that carbon is supposed to have. And we know carbon is supposed to have 4 valence electrons. So from that number, we subtract the number of valence electrons in the bonded atom, or the number of valence electrons carbon has in our drawing. But now we need to think about these covalent bonds as being ionic. And so the more electronegative atom is going to take all of the electrons in the bond. So we need to think about electronegativity differences, and we're comparing carbon to hydrogen. So which is more electronegative? We know that carbon is more electronegative than hydrogen. So the 2 electrons in this bond here, carbon's going to take both of them. So it's winner takes all. Carbon's going to hog those electrons in this bond. All right, same for this next carbon-hydrogen bond. Carbon is more electronegative, so it takes those electrons, and all the way around. So we can see that carbon is now surrounded by 8 electrons, right? Let's count them up here. 1, 2, 3, 4, 5, 6, 7, 8. So 4 minus 8 is equal to -4. So we already knew that -4 was going to be the oxidation state for carbon. Let's move on to another molecule here. So C2H4, this is ethene or ethylene. What's the oxidation state of carbon in this molecule? Well, hydrogen should be +1, and we have 4 of them for a total of +4. So the total for carbon should be -4 because that total has to sum to 0. But this time we have 2 carbons. So -4 divided by 2 gives us -2. Each carbon should have an oxidation state of -2. Let's verify that, right? Let's put in our bonding electrons and let's calculate the oxidation state of carbon by using our little formula here. So we put in our bonding electrons, and let's just pick one of the carbons to start off with. Let's say we're talking about the carbon on the right. So we think about electronegativity differences, and we know carbon's more electronegative than hydrogen, so carbon's going to steal those electrons. And same thing over here, carbon's more electronegative, so carbon steals those electrons too. When we get to this double bond here between the 2 carbons, we have these 4 electrons, and now we're trying to compare the electronegativity of carbon to carbon, and obviously that's the same electronegativity. So with 4 electrons, we're going to divide those electrons equally because both those carbons have the same value for the electronegativity. And so we take those 4 electrons, we divide them in half. So we give 2 electrons to one carbon and 2 electrons to the other carbon. So carbon normally has 4 valence electrons, right? So we're using our formula here for oxidation state. Oxidation state is equal to the number of valence electrons that carbon is supposed to have minus the number of valence electrons around carbon in our drawing. So let's count them up after we've accounted for electronegativity. That's 1, 2, 3, 4, 5, and 6. So 4 minus 6 gives us an oxidation state for carbon of -2, which is in agreement with what we calculated over here. Keep in mind that each carbon was supposed to have an oxidation state of -2. So if we look over here at the carbon on the left, right, and we just assign those electrons really quickly, we can see that that would be the same calculation. 4 minus 6 gives us -2. So each carbon has an oxidation state of -2. We move on to another molecule, so CH2O, this is formaldehyde, And we know that oxygen usually has an oxidation state of -2, and we have one oxygen for a total of -2 down here. Hydrogen usually has an oxidation state of +1, and we have two of them for +2. This total has to sum to 0, so carbon should have an oxidation state of 0 in this molecule. Let's go ahead and look at the dot structure, right? We put in all of our bonding electrons so we can find the oxidation state easier. And we think about electronegativity differences. We know carbon's more electronegative than hydrogen, so carbon takes those electrons, right? Same for this bond, carbon takes those electrons. But now we're going to compare carbon to oxygen, and we know oxygen is more electronegative than carbon. So oxygen's going to take all of those electrons, so all 4 of those electrons in that double bond. So it's winner takes all when you're thinking about oxidation states. Right? So because oxygen is more electronegative, it takes all of those electrons. And now we can see that carbon is surrounded by 4 electrons. So 1, 2, 3, 4. Carbon is supposed to have 4 valence electrons around it, and here we see it is surrounded by 4 once we take into account electronegativity. So 4 minus 4 gives us an oxidation state of 0. So in the formaldehyde molecule, carbon has an oxidation state of 0, which is what we predicted over here. Let's think about oxygen, right? We said that oxygen would have an oxidation state of -2. So let's look at oxygen. Oxygen's right here. And let's think about how many valence electrons oxygen should have. Well, because of its position on the periodic table, oxygen should have 6 valence electrons. How many electrons are around it now once we've accounted for electronegativity? Well, here's 1, 2, 3, 4, 5, 6, 7, and 8. So 6 minus 8 gives us an oxidation state for oxygen of -2. What about for hydrogen? Right, so hydrogen should have 1 valence electron, but there's 0 electrons around it here because carbon's more electronegative than hydrogen. So 1 minus 0 gives us an oxidation state of +1, which is what we predicted over here. And the same thing for this hydrogen. So this formula works for other atoms too. All right, let's do another example, and this time we're doing formic acid, so CH2O2. Oxygen should be -2, and we have 2 of them, so we have -4 for totaling our oxygens. Hydrogen should be +1, and we have 2 of them for a total of +2. And now this total has to add up to equal 0, so we know that carbon's oxidation state should be +2 in the formic acid molecule here. So let's go over and put in our bonding electrons. Right? So we put in all of our bonding electrons here, and we think about the oxidation state of carbon. We think about electronegativities. So carbon's more electronegative than hydrogen, so carbon gets those 2 electrons in that bond. But over here, oxygen is more electronegative than carbon, so oxygen takes those electrons. And the same thing above. Oxygen's more electronegative than carbon, so oxygen takes those electrons too. So what's the oxidation state of carbon in formic acid? Well, carbon is supposed to have 4 valence electrons, and from that we subtract the number of electrons around carbon once we've accounted for electronegativity, once we pretend like everything is ionic. And that's only 2 electrons this time, so 4 minus 2 gives us an oxidation state for carbon of +2, just like we predicted over here. So you can see every molecule we've done so far has had a different oxidation state for carbon. Carbon is unique, right? It has all these different oxidation states. Let's finally look at carbon dioxide. So oxygen should have an oxidation state of -2, and we have 2 of them for a total of -4. So carbon must have an oxidation state of +4. So we look at our dot structure over here, and we put in our bonding electrons, and we think about electronegativity. Oxygen is more electronegative than carbon, so oxygen is going to steal, each oxygen is going to steal the electrons in those bonds. So let me redraw it here. I'll show oxygen I'll show oxygen with all these electrons around it. So the 4 electrons in that double bond here are all going to be on this oxygen on the left. Same thing for the oxygen on the right. It has these lone pairs of electrons, and it's more electronegative than carbon, so it steals all of those electrons, which leaves carbon with 0 electrons around it. So to find carbon's oxidation state, we know carbon should have 4 valence electrons, and here, we have 0 electrons around carbon. So 4 minus 0 gives us an oxidation state of plus 4, just as we predicted. And if you wanted to do each oxygen, oxygen should have 6 valence electrons, and here we have 1, 2, 3, 4, 5, 6, 7, 8. So 6 minus 8 gives us minus 2 for the oxidation state of oxygen. All right, let's go back up to the beginning here, Let's look at all these different oxidation states that we've covered for carbon. So we started off with an oxidation state for carbon of minus 4, we went to minus 2, and then we went to 0, and then we went to plus 2, and then finally we ended up with plus 4. So carbon can have a range of oxidation states from minus 4 to plus 4 when you're talking about carbon with 4 bonds. And you can also have in between, It's possible, of course, for carbon to have an oxidation state of plus 3. I just didn't do an example like that in this video.